Somewhere in Munich right now, there is a machine running that does not use electricity to think. It uses light, not fiber optic cables carrying data between 2 points. Light itself, doing the math. For 70 years, every computer on Earth has worked the same way. Push electrons through copper. Faster electrons, faster computer. But that trick is dying. The transistors inside the most advanced chips on the planet are now so small that electrons start leaking through walls that are supposed to stop them through a process called quantum tunneling. Push more power in to compensate, and the chip cooks itself. Engineers call this the power wall. And in a very real sense, it is the wall that decides who wins the next decade of artificial intelligence. So a strange collection of startups, spin-outs, and national labs across Germany, the United Kingdom, the United States, and Canada started asking a different question. What if you stopped pushing electrons and started bending light instead? That question is not theoretical anymore. As of this year, there is a working photonic coprocessor bolted into a real operational supercomputer doing real physics simulations for real researchers right now. This is the story of who is actually winning that race, who has already failed trying, and why a chip that computes with light might end up mattering more to the next chip war than anything happening in Taiwan. To understand why anyone would bother building a computer out of light, you first have to understand exactly where electronic computing breaks down. Modern processors move information by driving electrons through interconnects and transistor channels that are now measured in single-digit nanometers. Below about 3 nanometers, 3 things start working against you at once. Quantum tunneling leakage, where electrons slip through barriers they shouldn't. Resistive heating, where the sheer density of switching transistors generates more heat than you can practically remove. And something called RC delay, where the resistance and capacitance of the copper wiring itself starts to slow the signal down, no matter how fast the transistor underneath it is. Put those 3 together and you get diminishing returns. Every new generation of chip costs more, uses more power, and gains you less than the last one did. That combination has a name in the industry, the silicon ceiling. Photons do not have this problem for a simple physical reason. They have no electric charge. 2 beams of light can cross paths inside the same optical channel without interfering with each other the way 2 currents of electrons would. On top of that, you can send many different wavelengths, essentially many different colors of light, down a single waveguide at the same time, each one carrying its own independent stream of data. That trick is called wavelength division multiplexing, and it is one reason photonic systems can move so much more information through so much less physical space. And because light does not generate resistive heat as it travels through a passive waveguide, the thermal cost of moving data drops dramatically. None of this means we're about to throw away silicon. What is actually happening is more interesting than that. In every serious photonic architecture being built today, ordinary silicon chips still handle logic, memory, and instruction control. Light is being used specifically for the part of computing that silicon is worst at: massive, repetitive matrix math. The kind that dominates artificial intelligence training, scientific simulation, and signal processing. So who is actually building it? Because the honest answer is, there is no single winner yet. There are at least 4 completely different bets being placed on how to make light compute, and 4 different companies leading each one. Start in Stuttgart, Germany, with a company called Q.ant. In July of 2025, Q.ant delivered what may be the single most important milestone in this entire race so far: the first analog photonic coprocessor ever installed inside an operational, real-world supercomputing facility, the Leibniz Supercomputing Center near Munich. Not a lab demo, a working card in a working machine, funded by Germany's Federal Research Ministry. By March of 2026, Q.ant had deployed a second generation of that processor, and the improvement was not subtle. 50 times higher throughput on matrix multiplication, 25 times faster inference on a standard image recognition network, and roughly 6 times lower energy draw for typical workloads compared to their own first-generation chip less than a year earlier. That is the kind of generational leap silicon stopped delivering years ago. Now go to the United States, to a company called Light Matter, which is, by funding, the giant of this entire space. Valued at $4.4 billion, backed by Google Ventures, Lockheed Martin, and HP Enterprise, among others. Light Matter's approach is different from Q.ANT's. Instead of one accelerator card, they are building the interconnect that lets thousands of chips, GPUs, TPUs, whatever you have, talk to each other through light instead of copper. Their Passage platform is a three-dimensional, wafer-scale optical interposer, and in a peer-reviewed paper published in the journal Nature, Light Matter demonstrated a system with 50 billion transistors and roughly 1 million photonic components, executing real deep learning models while drawing just 78 watts of electrical power and 1.6 watts of optical power. Then there is Lumai, spun out of Oxford University in the United Kingdom, which took an almost contrarian bet. Lumai looked at the crowded, lossy, two-dimensional silicon waveguides everyone else was cramming light into and said, that is the wrong shape. Instead, they built a free-space, lens-based optical computer that does its math inside a three-dimensional volume. In April of this year, Lumai launched a server called Iris Nova, and it did something no one else had done yet. It ran real, billion-parameter large language models, including Meta's Llama models, in real time using light, while cutting power consumption by 90% compared to a standard GPU cluster. And then there is the most radical bet of all. A Berlin-based company called Photonics, backed by Germany's Federal Disruptive Innovation Agency. Every system we've just described is hybrid. Data gets converted from electricity to light and back again, constantly. Photonics is trying to skip that conversion entirely, building a general-purpose processor where logic itself happens optically, with no electronic conversion in between. In February of 2024, they demonstrated a working 2-bit all-optical CPU running actual classical software entirely in the optical domain. 4 companies, 4 completely different physical philosophies, and, so far, no single one of them has definitively won. Here is where I have to slow down, because this is the part most coverage of photonic computing conveniently skips. Every one of these systems still has to convert data from electrical signals into light, and then back into electrical signals again to actually be useful. That conversion loop, digital to analog, electrical to optical, optical back to electrical, analog back to digital, has a cost. Researchers publishing in the journal Optics Express found something uncomfortable for this entire industry. Unless the actual optical math being performed is extremely dense, the energy spent on that conversion loop can outweigh the energy you saved by using light in the first place. There's an industry nickname for this: the conversion tax. And it's not the only bottleneck. Densely packed optical chips suffer from thermal crosstalk, where heat from one modulator bleeds into its neighbor and quietly corrupts the calculation. Waveguides lose signal to microscopic surface roughness as light travels through them. And the entire software stack that the rest of computing runs on, the compilers, the frameworks, everything built on top of NVIDIA's CUDA over the past 15 years, simply does not know how to talk to an optical chip yet. Someone still has to build that bridge industry-wide, and right now, nobody fully has. And if you want the clearest warning sign of how hard this actually is, look at a company called Luminous Computing. Backed early on by Bill Gates and other high-profile investors, Luminous raised over $115 million trying to pack an entire optical supercomputer onto a single chip. On December 17th of last year, they shut down completely. Their patents went inactive. The post-mortem is brutally simple. Cramming thousands of optical components onto one piece of silicon created layout congestion, thermal chaos, and packaging problems that nobody could solve at the scale they needed. The lesson the survivors learned from that failure is the same lesson showing up everywhere in this piece. Don't try to build one impossible chip that does everything optically. Build one very good optical accelerator for one very specific mathematical bottleneck and bolt it onto the electronic system that already works. There is one more wrinkle worth understanding because it explains why some of the loudest marketing claims in this space do not survive contact with peer review. Companies routinely advertise numbers like 100 times faster and 90% less energy than a standard GPU. Independent evaluation at the Leibniz Supercomputing Center tells a more grounded story. Under real production workloads, not cherry-picked benchmarks, Q.ANT's second-generation processor cut energy consumption by roughly 6 times compared to its own first generation. A genuinely significant improvement, but nowhere near the blanket 90% reduction the marketing implies. Because the host processor, the cooling system, and the rest of the server rack still draw power the entire time, the total system-level savings will always be smaller than the chip-level number a press release wants you to remember. So why should any of this matter to you, sitting outside the small circle of people who read supercomputing press releases for a living? Because this is quietly becoming the next front in the global chip race, and it is a front where the old rules don't automatically apply. The current chip war is fought over who can manufacture the smallest transistor. Photonic computing sidesteps that fight entirely. Q.ANT's chips are built on mature manufacturing nodes, not the bleeding-edge 2-nanometer processes that only 2 or 3 fabs on the planet can produce. That is a genuinely different kind of competition, one where funding, physics expertise, and government backing might matter more than owning the most advanced fab in Taiwan. Governments have noticed. Germany's research ministry funded the Q.ANT deployment explicitly as a matter of European technological sovereignty. The UK's National Research Agency is backing Lumai for the same reason. Marvell just spent $3.25 billion acquiring a photonic interconnect company called Celestial AI because NVIDIA and the rest of the AI hardware industry can see the same power wall coming that everyone else can. For a region like South Asia, watching this from outside the 2 dominant blocks of American and Chinese silicon manufacturing, the photonic shift is worth watching closely for exactly that reason. It is one of the very few frontiers in advanced computing where the manufacturing playing field has not already been locked up for a decade by a handful of fabs. Nobody has a 10-year head start here yet. There is also a second, stranger branch of this race running in parallel. One that barely gets mentioned alongside the accelerator companies. A handful of organizations are not just using light to speed up classical math. They are using individual photons themselves as quantum bits, trying to build fault-tolerant quantum computers out of photonic hardware. PsiQuantum, backed by a $750 million round led by BlackRock and selected by the American Defense Research Agency DARPA for the final phase of its quantum computing program, is building toward a system so large it is designed to occupy an entire data center floor, essentially a cryogenic photonic supercomputer in its own right. Toronto-based Xanadu has already launched a working 12-qubit photonic quantum system with active partnerships across Volkswagen, IBM, and NVIDIA. That branch of the race operates on a longer timeline than the accelerator cards being installed today, but it is being funded with exactly the same urgency for exactly the same underlying reason: the belief that the next decade of computing cannot be built on electrons alone. The honest, unglamorous truth is that nobody has built a fully optical, general-purpose supercomputer, and the strongest scientific evidence available says nobody is going to, not anytime soon. What is actually being built, verified, and deployed right now is something narrower and more useful. Hybrid machines, where silicon still runs the logic, and light gets handed the one job it was always physically better at: moving enormous amounts of data and crunching enormous matrices at close to the speed of light itself. There's something I didn't get into in this video: the quantum side of this same race, where companies like PsiQuantum are trying to build fault-tolerant quantum computers out of the exact same photonic components, backed by a $750 million round led by BlackRock. That is a different kind of machine entirely, and it deserves its own breakdown. If you want to understand exactly how that connects back to the chip war playing out across Asia right now, that's the next video to watch.